Okay, in this video, I'm going to discuss the complex ion, and I gave you a flavor of that in the last video where we discussed the silver chloride and how addition of ammonia changes things. So, we have discussed several types of equilibria so far. Acid-base solubility and complex is just another kind of those, but this will primarily involve a transition metal ion in solution. Now, transition metal ions tend to be good electron acceptors. So recall from chapter 15 that those are great Lewis acids. So let's write that somewhere. Transition metal ions. Let's write that as N plus because those could be variable charges. Those are great Lewis acids, and I'm calling them Lewis acids because they are electron acceptors. And in aqueous solutions, water molecules or ammonia, those can act as electron donors. So things like NH3, which has lone pair of electrons, or things like water. These usually are small molecules which have a source of electron, so these can act as electron donors. And hence, in that sense, they can behave as Lewis bases. And so, for example, hydration of transition metal ions can take place. So silver, for instance, can remain hydrated with water to give you AgH2O twice. The positive charge is going to be outside of the coordination sphere. A lot of times we would just write that as Ag plus and AQ, which basically means that it's a hydrated silver ion, but really realize that a bare ion does not exist by itself in solution. So again, the concept of H plus as AQ or H3O plus in reality. So species such as the Ag with the H2O, that entire unit is what is going to be referred to as the complex ion. So you can think about a complex ion to contain a transition metal ion, which will be the central metal ion, and it will be surrounded by small electron donors, small molecules like water and ammonia, which are going to be referred to as a ligand. Some people like to pronounce that as ligand, but it really is a ligand. A ligand is a neutral molecule or an ion which can act as a Lewis base for the central metal ion. So again, complexes will contain two things: a metal ion plus a ligand. So it's a combination of a Lewis acid and a Lewis base, if you will. So one can see that here water is going to behave as the ligand and silver was the metal ion, and together they formed the complex ion in this particular case. Now, consider silver as AgH2O2, and there is a positive charge, and you add ammonia to the system. What's going to happen is that ammonia is going to displace the water. So what we are saying is that a more stable complex, AgNH3, is going to get generated and is going to displace water from the system. So one can say that Ag plus can react with ammonia to give you AgNH3 twice with a positive charge, and if the formation constant for this Kf is 1.7 times 10 to the 7th. So formation constant is going to basically mean the silver diamine divided by silver times ammonia square of that. And if we're saying that the formation constant is a pretty high value, that basically tells you that the forward reaction is going to be more predominant as compared to the backward reaction. And so one can say that if the formation constant is large, then then the dissociation, that means the reverse reaction, is going to be pretty small. So what that means is that the backward reaction, that means AgNH3 twice with one positive charge, going and dissociating to give you Ag plus and 2 ammonia, that's going to be pretty highly unlikely. The Kd, the dissociation constant, which can be taken to be 1 over Kf, that's going to be 1 over 1.7 times 10 to the 7th. And so that value is going to be a pretty low number. And if I punch in on the calculator, and that gives me 0.58 times 10 to the negative 7, or 5.8 times 10 to the negative 8. Notice this is a really small number and tells you that the backward reaction is not going to be the more predominant one in this case. All right, let's take another scenario. All right, this scenario is for nickel. So nickel, like I said previously for silver, even for nickel, if you take an aqueous solution of nickel, Ni2 plus aqueous can be actually the actual species that's present there is the NiH2O6 with two positive charges. Now this is green in color, and if you take that and you treat that with 6 ammonia molecules, that ammonia molecule is going to displace the water out. Okay, and the Kf for that is 5 times 10 to the power of 8. And when you do the same thing with what is called as ethylene diamine, we abbreviate it as En, but it's actually ethylene diamine, which is this molecule. Essentially, the formation constant for that is 1.1 times 10 to the power of 18, and that is like a really high formation constant value. Now, this first one, the nickel complex with the ammonia, that has a blue color, and the ethylene diamine complex, that has a purple color. Okay, so let's discuss a little bit of the chemistry in this case. So this is what we are saying. We are saying that if we have a green solution of the nickel hydrate system and we add ammonia, the color should become blue. And so those of you who probably would have done this, lab in, which lab was that? Lab 16. So those of you who would have used a nickel would have seen that purplish blue type color. And the Kf for that is 5 times 10 to the power of 8. And when you do the same thing with ethylene diamine, it's actually much, much stronger. So hopefully you can see just by the comparison of these two reactions that the complex with the ethylene diamine is more stable as compared to the complex with ammonia. The complex with ethylene diamine, because of the structure, it's also called as a chelate. A chelate is nothing but a ring containing complex. Ring containing complex. The reason why I call it a ring containing complex is because if you consider nickel with ammonia, you would have to say that you have nickel and you have in 5 or rather 6 different directions as an octahedral, you're going to see the ammonia complex bind with it, right? On the other hand, if you were to do that for the diamine complex, you would say that a nitrogen and a nitrogen, and that forms a ring. Likewise, a nitrogen and a nitrogen, and the third one would be, I kind of made a mistake here. Yeah. and the third one would be right here. So realize that within the complex, I have these 1, 2, 3, 4, 5. 5 atom rings, which are pretty stable. And that is why, structure-wise, since these are stable compounds, these are chelates, and they're considered more stable than the corresponding open complexes. Also realize that we are forming these chelates because the ethylene diamine has two sites where the attack can take place on that nickel. And so we call this a bidentate ligand. Bidentate. Bi is for two, dentate for two sites or two areas where the teeth will bite the metal, if you will. So bidentate, so two hooks for the point of attachment. On the other hand, ammonia, you would say, is a monodentate ligand because there is only one nitrogen for the site of action. Okay? Okay, let's continue our discussion about the factors that affect solubility. That's how that entire section on complexes came into being. We were discussing the factors on that affect the solubility, and sometimes it could be a pH of the solution. So, for instance, if you have, let's say, marble is CaCO3 calcium carbonate, which is in equilibrium with Ca2 plus and a CO3 2 negative. CO3 2 negative. All my formatting is off because of this PC and Mac fight. Anyway, if you add a hydronium ion to the system, that means the carbonate will then start reacting with your hydronium ion, and it will generate a new equilibrium of its own that will give you bicarbonate and water. HCO3 negative and H2O. So realize if we are removing carbonate, that means the equilibrium is going to move in a direction to undo that effect. That means more and more marble is going to get dissolved. Where are we going with this? This is why acid rain is such a big problem. Because calcium carbonate or marble is used as a manufacturing material in lots of buildings, and there have been buildings, in the past, and sometimes cultural heritage. For example, the Taj Mahal, it's made purely of marble. Now, because of the acid rain, that extra additional hydronium ion reacts with the carbonate, and it's going to generate bicarbonate, which is going to cause the thinning down of that calcium carbonate and the dissolution of that. So, of course, now the government of India is taking steps, and for that matter, lots of statues in Italy, in Rome, would also go through the same thing. Older buildings in general used to utilize marble as a building material, and the problem there is that acid rain eats away the marble because it reacts with the carbonate, sets up its own equilibrium the way we showed, and that is going to force the equilibrium in the forward direction. That means more and more marble is going to get dissolved, and thinning down of that is going to take place. All right, let's also take a look at the effect of pH on calcium oxalate. Where would you find calcium oxalate? Any guesses? This is what is present in kidney stones. Kidney stones. And so calcium from your body and oxalate from food sources over a period of time is going to give you the precipitate of calcium oxalate. And now, if you eat a little bit acidic foods, such as, let's say, even drink milk for that matter, the lactic acid is going to, or yogurt, more importantly, the lactic acid is going to use up the oxalate, and so the forward direction equilibrium will be more pronounced. And so you might have heard the latest sort of cure is that they ask you to drink skimmed milk, is what they ask you to do. They don't want to kind of overpower, like provide too much of the calcium, but they're looking at the acidity of the lactic acid from milk, which will be able to use up the oxalate. And in general, the idea there is that if you have a salt which is of a weak acid, such as oxalic acid, so something like calcium oxalate will be soluble in acidic solutions. Based on that idea is also the tooth decay. That's based off of that as well. So our enamel is, and as well as bones, those are made up of calcium phosphate. And specifically in the enamel, it's a combination, it's a mineral that contains calcium phosphate as well as calcium hydroxide, both of those. When I view this, I view that as if calcium phosphate is sort of the bricks, and to bind those pieces is the calcium hydroxide, like a cement. And that's how the wall gets strong. This mineral is called as hydroxyapatite. Hydroxyapatite. Now, when you eat two acidic foods, so if you drink, I don't know, like 5 Pepsis or 10 Pepsis a day or something like that, or if you don't brush your teeth, or if you eat too much sugar, because sugar over a period of time after oxidation is going to generate the acid, the H plus is going to react with the OH minus and is going to basically eat away the calcium hydroxide, is going to neutralize that. So you can then envision that the calcium phosphate is by itself. There is nothing there to bind it. Okay. Now, what happens in presence of when you actually brush teeth? Good toothpastes, they deliver. If you look at the active ingredient, you will see sodium fluoride. And especially in regions which do not have enough fluoride content in water, there should be some fluoride. You're not supposed to ingest too much of it because too much fluoride is poisonous for you. But it's actually good for you if you rinse your mouth with that, because that F negative is going to replace the OH, and what you're going to see is calcium phosphate and CaF2. So that's called what is called as fluorapatite. Fluorapatite. And CaF2 is more insoluble than CaOH whole twice, because of which the effect of the acid from the acidic foods is not going to be as predominant as it would have been with just enamel. So by using sodium fluoride containing toothpastes, you can actually prevent tooth decay and you can prolong the life of your enamel. Let's consider the milk of magnesia example. So dissociation of MgOH whole twice, which is the active ingredient in milk of magnesia, Mg2 plus and 2 hydroxide is going to get generated, aqueous and solid. And so the solubility of this compound is highly dependent on the pH of the solution in which it is dissolved. If the pH is high, that means we have more of the hydroxide. So high pH, if pH is high, that implies greater amount of hydroxide, and that would mean the backward reaction would be triggered, and hence, because of the common ion effect, the equilibrium will shift to the left and the solubility will be low. On the other hand, if the pH is low, then the concentration of the hydronium is going to be high. And that is going to use up the hydroxide. That means more and more magnesium hydroxide will have to dissociate, and it will drive the reaction to the right. So consequently, the solubility of the magnesium hydroxide in an acidic solution is higher than in a pH neutral or a basic solution. So in your bottle of milk of magnesia, you might see some, some solid, some precipitate, but as you drink it, for the acidity, essentially it works because the forward equilibrium is then more predominant, which generates the OH minus. So in general, again, solubility of an ionic compound with a strongly basic or weakly basic anion increases with increasing acidity. And we did the marble example, based on which is also the stalagmite stalactite. We did the tooth decay, we did the kidney stone, and the milk of magnesia. All of these are basically driving the equilibrium along the directions. The general idea being that if you have a basic anion, then the solubility is going to be more if the if the pH is going to go down. So if the hydronium ions are there. Okay, let's see if we can apply this. The question is, determine whether each compound is more soluble in an acidic solution or in a neutral solution. So whether acidic versus neutral, which one is more soluble? The first one is BaF2. BaF2 will have an equilibrium between barium and fluoride, and hopefully you can see that if you have F minus, that basically is a weak base of the conjugate acid HF. And so if you increase the proton concentration, you're going to remove the F negative. What that would mean is that more and more BaF2 would then tend to dissociate, and the solubility will increase. So solubility will increase as acidity increases. AgI is going to give you Ag and I minus. In this case, realize I minus is not like a fantastic base. The corresponding ion is Hi, which is a strong acid. So the conjugate base is like barely basic. So since Hi is a very, very strong acid, hence you would say that this is not going to get affected by an acidic solution. The third one that we have here is calcium hydroxide. Again, that's going to be Ca2 plus and 2OH negative. The OH negative is going to interact with the H plus, and hence it will be, the solubility is going to be more. Solubility increases as acidity increases in this case as well. All right, let's work on. Okay, I now want to take the time to talk about amphoteric hydroxides, which are basically metal hydroxides that can react both with acids as well as bases. So for example, zinc hydroxide that can react with more OH negative to form the zincate ion. On the other hand, it reacts with the H plus to generate Zn2 plus and water. Likewise, AlOH whole thrice that can also dissolve with the base to generate aluminate. And so realize that some hydroxides, some metal hydroxides, will have the ability to behave as an acid or a base. To kind of dig a little bit deeper, I mean, why would aluminum hydroxide behave the way it does? I mean, hydroxides in general, many metal hydroxides are insoluble or very partly soluble in a pH neutral water. So same is the case in case of ALOH whole thrice as well. It's not very soluble. It in fact has a KSP of 2 times 10 to the power of negative 32. Oh my goodness, you put the zeros. They're just way too many for me to write here. It's 2 times 10 to the negative 32. It's a very, very small number. That means if you put aluminum hydroxide in water, the vast majority of it is just going to settle as an undissolved solid, and not much is going to happen there. Now, they will provide, the metal hydroxide will have a basic anion, the OH negative. And so if you add H plus to that, of course that H plus is going to start reacting with the OH negative, and so you would see dissolution of that hydroxide. So it becomes more soluble. That means the ALOH whole thrice is going to behave as a base when an acid is added. So your reaction becomes ALOH whole thrice plus 3H3O plus gives you aluminum plus 6 water. On the other hand, this ALOH whole thrice also can be treated with excessive amount of the hydroxide, and that's when it gives you the aluminate. And that's possible too. It's a complex ion that gets generated, but it's a possibility. And so we say that the ALOH whole thrice in that case is going to behave as an acid. So since it was earlier behaving as a base in the first reaction with hydronium, and now it's behaving as an acid when it's treated with the hydroxide, we say that ALOH whole thrice has amphoteric behavior. So amphoteric again just means the ability to be able to behave as an acid as well as a base. Now I'm going to spend some time in going over some math problems which will kind of tie in the complexometric, the KSP possibilities, all of that kind of together, and we'll take it from there. Okay, so the first question is, what is the concentration of silver ion in 0.01 molar AgNO3 that is also 1 molar ammonia? So first things first, silver nitrate is going to completely dissociate and give you Ag plus NNO3. But realize that this Ag plus is not going to remain as Ag plus. That Ag plus will be instantaneously picked up by ammonia because you have too much of it, and it's going to generate your AgNH3 twice. So there's an equilibrium that's going to get generated right there. Now the question is, they're asking the concentration of Ag plus. So realize initially the concentration was 0.01 molar for silver, and so this was 0.01. And ammonia is 1 molar, but from that 1 molar, 2 times the 0.01 would have essentially reacted with the silver in order to carry out that complexation. So we are beginning with sort of 0.98 molar solution for ammonia because that has reacted. And so if you were to think about, since this is the formation constant, so if you were to think about the dissociation, because realize the free silver is what we are after, and the free silver can only be obtained if the silver diamine is ready to go through a dissociation reaction. And hopefully you can see. So hopefully you can see that since the NH3 is, you have a boatload of it, and the limiting reactant is the Ag plus, all of that is going to generate the diamine complex. So your initial concentration of the diamine complex is going to be 0.01. Of course, you won't have any silver, but you are going to begin with 0.98 as the concentration for ammonia, because a little bit of it has been utilized in the complexation process. Now let's say the change for this dissociation is by x moles. That would give you x moles of silver and 2x of the ammonia. That means at equilibrium you're going to find 0.01 minus x of the complex, x of the silver, and 0.98 plus 2x of the ammonia. Once you have established this, now it's just time to set up your KD. So let's maybe utilize this space for that. So you would say that the formation constant, which is the value that is provided in the question, the formation constant, which would have been silver complex divided by, this is plus, divided by silver concentration and ammonia square, and that value is 1.7 times 10 to the power of 7. Now the opposite, the inverse of that, is going to be KD. So KD is nothing but 1 over KF. And so you can simply set up the equilibrium for that as Ag, which is x times 0.98 plus 2x square of that divided by the 0.01 minus x, and that should be equal to KD, which is 1 over 1.7 times 10 to the power of 7. I have a feeling I have calculated this before, but anyway. Let's basically solve for x. Hopefully you can see that you would be able to use the approximation. X is going to be too small. So you can say that this basically should boil down to x times 0.98 square of that divided by 0.01, which will be equal to 5.9 times 10 to the power of minus 8, negative 8. And so when you solve this, the value of x will come out to be 6.1 times 10 to the power of negative 10. Now that's the itty bitty, really small value. But that will be the concentration of silver plus, of free silver plus, which also contains a boatload of ammonia. We had 1 molar solution of ammonia in our system. All right, let's take a look at another question. The question is, calculate the molar solubility of AgCl in 1 molar ammonia. So you have AgCl, which is solid, and gives you Ag plus and Cl negative. So that's your equilibrium right there. Now realize that the Ag plus that you have, that's not going to just stay like that. Because it contains ammonia, it is going to dissolve in that. It is going to react with it. And you have another equilibrium, which is the formation constant. Now for the first reaction, the KSP for that, so for this the KSP is known. For the second reaction, the formation constant is known. Hopefully you can see that if you add the two, because these are the two reactions that are ongoing, if you add the two, the silver and silver will cancel off, and AgCl plus 2 ammonia is going to give you the silver diamine complex and the Cl negative. So when you add the equations, you should take the product of the K value. So Kf times Ksp should be equal to the K for this desired reaction. So hopefully you can see 1.7 times 10 to the power of 7 times 1.8 times 10 to the power of negative 10, and that value comes out to be 10 to the negative 3, and these two when multiplied give you 3.1 times 10 to the negative 3 as your answer. Now, realize this is only the K value, okay? Now, the question asks you for the molar solubility. That means how much of the AgCl is essentially in the solubilized form. So you can, if you look at the equation, if you determine the free Cl, or the silver which would have later on gotten in a complex formation, you would be able to determine the solubility from there. So you have to solve an ice problem in this case. So realize you're beginning with, of course, AgCl, which is a solid and is not going to participate directly. Ammonia is 1 molar. So your ice with AgCl plus 2NH3, giving you AgNH3 twice and Cl negative. So this is 1 molar. You don't have any complexation in the beginning. If 2x are involved, that would mean x of the products would get generated. So you're going to be left with 1 minus 2x for the ammonia, x for the complex, x for the chlorine. And we are going to plug this in for our system. So I would say x squared divided by 1 minus 2x is going to be 3.1 times 10 to the negative 3. And since 2x is this is a linear equation because both of these are squares, you should be able to determine x over 1 minus 2x is equal to 0.056, and when you solve for x, let me just punch in the numbers. I am getting 0.05. So that tells me that the AgCl, the molar solubility of AgCl equals the molar concentration of silver in the solution. And because of the stability of the diamine complex, most of the silver is going to stay as the complex ion, and that will also be equal to the concentration as well as the molar solubility, and will be 0.05 molar. Okay. All right, let's solve another question. The question is you have to calculate the solubility in grams per liter for CaF2 in water from the solubility product constant, which is given 3.4 times 10 to the negative 11. We've done such examples, and again, your dry lab will provide you more practice. But I just thought I'll wrap it up with a couple more solubility questions. The more you do, the better you get. So your equilibrium, again, to remind you, is CaF2, giving you calcium and 2 fluorides. So if you consider the ice, you don't have any of the products in the beginning, then you have X, and so at equilibrium you're going to end up with X and 2X. What that means is the Ksp, which is going to be Ca2 plus times F negative square of that, you would say X of 2x, X times 2x whole square, that is 3.4 times 10 to the negative 11. And when you work out the math, that gives you 3.4 times 10 to the negative 11. And so X comes out to be 2.0 times 10 to the negative fourth. So basically you divided both the equations by 2 and then took a cube root. This value is a molar. This is moles per liter. You have to convert it into grams per liter. What that means is that you will need to multiply this by the molar mass, which is calcium is 40, each fluorine is 19, so 19 times 2 looks like it comes out to be 78 grams per mole. So when you multiply, the value comes out to be 1.6 times negative 2 grams per liter of the CaF2. You can, if you want to, do a quick check once you have the moles per liter, and that's the value of X. Just, get the 2X and try to calculate the KSP and see if you're getting the same number or not, just to make sure that your math is fine. All right, let's do another one. Let's take a look at another one, and I think this is going to be the last one. Molar solubility of CaC2O4 in 0.15 molar CaCl2. So my equilibrium is for calcium oxalate, and I'm saying that I already have some CaCl2 in the system, so hopefully you can see that the backward reaction will take place, so your molar solubility should decrease. So qualitatively, it should decrease. I have been given the molar solubility in water, which is 4.8 times 10 to the negative fifth molar. So I'm expecting that now my value should come out to be lesser than what I have. Now, if you had to set up the ice for this case, of course, calcium oxalate is your solid and your aqueous are with calcium and the oxalate. Since calcium chloride is going to completely dissociate, your initial concentration of calcium is 0.15. There is no oxalate in the system. X moles of each of calcium and oxalate are present, and that would mean 0.15 plus X times X is going to give you the KSP. So you can say 0.15 plus X times X is the KSP, and the KSP value is given to be 2.3 times 10 to the negative fourth is 0.15 plus X times X. So now you would basically rearrange this. 2.3 times 10 to the negative 4 divided by 0.15 plus X, and since X is so small, you can simply use it, you can simply neglect it, and so when you solve it, the value of X is going to come out to be 1.5 times 10 to the negative 8. I miswrote that, so I fixed that. Okay, so notice this number that I have gotten. This is much lesser as compared to what I had previously in just pure water, and that makes sense. So my my thought is fine. Molar solubility, or in this case, has decreased as compared to what it was in pure water.